I'm continuing my series on solving some of the hardest mathematics exams from across the world, and today we're looking at the University of Oxford's admission test to study mathematics. Let's dive straight into it. Okay, amazing. So here is the paper. I have chosen the paper from October 2023. Firstly, what's worth noting is the exam itself is 2.5 hours. So it says here it's 2.5 hours. And you might have noticed that, yes, we have the University of Oxford here, but we also have the University of Warwick and Imperial College London. So I know that the admission test, this itself, the MAT for the University of Oxford, is required if you want to study mathematics at the University of Oxford and some other degrees as well that I think integrate maths within it. As for the University of Warwick and Imperial, I believe that this is not compulsory, but taking it does improve your chances of getting selected. So yeah, let's take a look at the full paper and then we'll dive into some of the questions. So as I said, the time allowed is 2.5 hours. Now feel free to pause the video and have a read of all of this here. The important thing to note is essentially this is saying that depending on what you're applying to Oxford for, these are the questions you must answer. So for us today, because we are focusing on the mathematics side of things, these are the questions that you would attempt. But if you're applying for computer science, then you would essentially not attempt question 4 and you'd attempt question 6 instead. So question 1 is essentially all multiple choice, but don't get too excited. They're not the easiest multiple choice questions, but I'll just zoom out a little bit. So we've got A, B, C, D, E, F, G, H, I, J, and yeah, that's it. And then questions 2 to 6, obviously depending on which you'll take, but for us it'll be 2 to 5. They're kind of just similar questions really, just standalone blocked questions. So this is question 2, this is question 3, this is question 4, this is all of question 5, and this is all of question 6. So as you can kind of see, in fact that's all of question 6. As you can see for question 6, this looks a little bit more suitable for people who are off to study computer science. So that's the entire paper. Like I said, feel free to pause, attempt some of the questions yourself. I highly encourage everyone to attempt these questions before watching the video, just so you can get a feel of how hard it is yourself, because it's a lot harder to attempt questions yourself than watch someone go through it. We're just going to dive into a couple of the questions. I've already answered a few of them, and I'm just going to walk through my solutions now. So we're going to start nice and easy. Well, I say nice and easy, maybe not easy for everybody, but I'm going to start with the first question in the exam itself. It's worth 4 marks. It's the multiple choice, so question A of question 1. And what it says in the question is we write that alpha is log base 10 of 2, and beta is log base 10 of 3, and gamma is log base 10 of 7. It says each of the following numbers is close to an integer. Which is the closest to an integer? So let's stick with A. So A is just 2 beta. We're told what beta is. It's here. So we can say 2 beta, which is what we've done here, is log base 10 of 9. And the reason for that is because if we have 2 of log base 10 of 3, that's the same as log base 10 of 3 squared, which is log base 10 of 9. And so that's where we get this value from. Now we can do something very similar for the rest. So let's look at B, which is 5 alpha plus beta. So this is log base 10 of 2 to the 5, like we've just shown, because obviously we've taken the 5 out the front here and put it to the power. So we've got log base 10 of 2 to the 5 plus log base 10 of 3, because that's what beta is. And then because we're adding logs together, we can multiply them, because that's essentially the definition. So log of A plus log of B, obviously they have to be in the same base, is log same base, A multiplied by B. So that's what we've done here. We've multiplied 2 to the 5 by 3, which is what we see here. We can compute that, 96. Now what we've utilised here is we're basically saying that, okay, well log base 10 of 96, that's the same as log base 10 of 10 multiplied by 9.6, which we can write, again using the powers of logs, as log of base 10 of 10 plus log base 10, 9.6, and we know that that's 1 and then we have the log base 10 of 9.6. So essentially that is what we've done here. We've utilised, simple laws in logarithms. Amazing. So following this, we get different values for a, b and c, and all we do is we look at the values inside of the logarithms here. So we have 9, 9.6, 9.8, 9.72 and 8.4, and quite clearly we can see that the one that is closest to 10 is 9.8, and so the answer is C. Now, like I said, feel free to pause this and just work through the maths yourself if it didn't come straight away, because I realise I've skipped over a couple of steps here, because the process is pretty similar for each of the A, B, C, D and E here, and yeah, hopefully you can get the same answer. We're going to move on to question B, and then we're going to move on to some of the later multiple choice questions, just because I'm conscious of time for this video. So question B says, exactly one of these 5 numbers is a square number, which one is it? Now we have each of these numbers here, and we can just work through them and deduce some things about them. And the kind of nice thing in this question is you can deduce which is the square number by process of elimination, which is quite nice. So here we have A, which is this value. Now, hopefully you'll know that this is 100 million minus 1, and hopefully you'll know that this itself is actually a square. It's 10,000 squared. And so we can say, well, no, this is actually one value off a square number, so it's not that one. Now, this one we can look at the end value. So this number ends in a number 3, and we know that no square ends in a number 3, so therefore this gets eliminated. We're going to leave C, because that, as you can kind of guess by the circle that's around it, that is the answer. But we're going to move on to D. So D has 35 at the end, and this itself is not actually a multiple of 25, and for that reason it's not a square number, so that's not true. And the final number here, you can just spot a very nice trick, which is basically saying that this is actually a multiple of 1,000 and not 10,000, and therefore it cannot be a square number. So, yep, that one's not true. And so because we've said, well, these aren't square numbers, it leaves by the power of deduction that this is the square number here. Now, I'd love to hear other people's approaches to this in the comments, so feel free to comment below and provide me with alternate approaches to how you would have figured out which was the square number. So question G says the real numbers A, B and C are non-zero. So we can first say, well, A, B and C do not equal 0, so they're non-zero. And we have that each of the following quadratic equations has a repeated real root, not necessarily the same value, so they have a repeated real root. Now, hopefully, from mathematics, you'll know that if we have a repeated real root, like I've said here, that implies that b squared equals 4ac for the standard quadratic formula. So that's for if we have a quadratic equation where we have ax squared plus bx plus c equals 0. So we'll have that b squared equals 4ac. Now what you might notice is, in this question we have the following quadratic equations. So we have the standard form of the quadratic equation here, as I just wrote out, but we also have a different equation here. It's still a quadratic equation, but just b, c and a are, different places. And the question says, how many distinct real roots does the equation of this have? And then, we have to determine whether it's 0, 1, 2, 3, or it depends on a. So like I said, we have a repeated root. So if we have a repeated root, we can look at the quadratic equations here and deduce things from them. So immediately from this quadratic equation, we can say, well, b squared equals 4ac. And from this quadratic equation, we can say c squared equals 4ab. Now, we do a little bit of manipulation here, essentially multiplying this by b, multiplying this by c, rearranging. By doing that, we find that b squared equals c squared, and so we have that b equals 4a and c equals 4a. Amazing. Now, because we know what b and c are here, this is going to help us when we look at this quadratic equation here. So we write down the quadratic equation that it says that we want to find out how many distinct real roots does it have. Okay, so if we want to look at the distinct real roots, we're going to look at the value inside the square root of the quadratic formula. So for us, we have, typically it would be b squared minus 4ac, but because our letters are labelled a bit differently here, we end up having a squared minus 4bc, which is what we've written here. And because we know the values for b and c, we can substitute them into there, rearrange, and what we find is that a squared minus 4bc is actually minus 63a squared. Because we know that a squared is always positive, minus 63 of a squared is going to be negative, so less than 0. We know that it's less than 0 rather than less than or equal to 0 because we're told at the start that a is non-zero, so therefore it's less than 0. Because we know that the determinant is less than 0, we can deduce that there are no real roots. And so the answer to this is a, because a is 0, and so there are 0 real roots to this quadratic equation. I actually really like this problem. I think it was one of my favourite out of the few here. Now instead of doing h, I've decided I'm going to do I instead, just because I quite like the maths in it. So h, here is the solution to h. Feel free to pause it and take a look yourself. But we're going to look at question I now. So question I says that the polynomial p of x has degree 3 and has that p of x equals 0 is 0. P at x equals 1 is 1, and P at x equals 2 is 2. The polynomial has a repeated root at x equals m, with m greater than 0, and it says to deduce what the value of m is here. So the first thing that stands out to me is that we have a repeated root at x equals m, so we're told that here. So immediately we can rewrite P of x in this format here. So I'm just going to move this just to say that that's P of x. So if we say that the repeated root here implies that P of x equals some constant, then we have x out front and we have x minus m squared. Now you might be wondering, well, how come we had it in this format and we didn't have, a of x minus, let's say, x1 multiplied by x minus m squared? And so one of the first things that we can kind of do is look straight away that we have that p at x equals 0 is 0. And so when we put x equals 0 into here, we must have that this whole thing turns into x equals 0. And so hopefully by just simple deduction, you can say, well, if we have x out front here, we know that p at x equals 0 is 0 because this cancels everything. And, we can verify that there. So we can write P of x in this format here by noticing two things, and that's that we have a repeated root at x equals m, and also just taking advantage of this here, that P at x equals 0 is 0. Now all that's left to do is substitute for x equals 1 and x equals 2 in, because we're told what P is at those values, and in doing so, that's what we do here. We essentially find two equations in terms of a and m. Because they're simultaneous equations, we can rewrite them and eliminate for a, which is what we do. And so we find this form here, so this equation for m, and by simple mathematical deduction here and here and here, we essentially arrive at m equals 3 over 2. Now feel free to pause and take a look at this, but essentially all we've done is we found this equation here from this, and then we've evaluated the plus or minus and considered which is realistic here. Because the first case, when we have the plus, we find that 1 equals 2, which obviously doesn't hold. That would be interesting in mathematics if it did. And then when we take the minus value, we end up with m equals 3 over 2. And so we find that the answer is E. Amazing. Okay, so that's it for the first question. Now I'm going to move on to one of the main questions in the paper, and we're going to look at some of the maths behind that. I am going to be making some separate videos on mathematics exams in Oxford and Cambridge because I love the style of questions they have, so subscribe for that. But let's move on to one of the main questions in this exam. Okay, so we're going to look at question 2. There's quite a lot of maths here, as you can see, but one of the first things basically we're told is we have n is a positive whole number. For x not equal to 0, we have this equation for Pn of x. So essentially this can change according to what value of n is put into here, and of course what value of x is also put into there. So this is crucial to the question. Now the first part of the question says sketch the graph of y equals p1 of x and label any turning points on your sketch. So I've just noticed that I didn't actually label any of the turning points, but I can do that as we as we walk through it. So basically what we do is we say, okay, well, we want y equals p1 of x. So we're wanting for when n is 1. And so we can put n is 1 into this equation here. And we find that p1 of x is x plus 1 over x for x not equal to 0, which obviously makes sense because we can't have 1 divided by 0 because that's undefined. So what we can do is straight away we can compute dy by dx. So let's see at what value the differential is equal to 0, which obviously is known as a turning point. And so when we compute the derivative of this, we find this, set that equal to 0, and we find that, well, this is true when x is plus or minus 1, and therefore when x is plus or minus 1, we find that p1 is plus or minus 2. So I should just label on the sketch here that this is, we had x as 1, 2, and this is minus 1, minus 2. Amazing. Now, we need that, so immediately straight away we can say, well, we figured out the turning point, so there's a turning point, there's a turning point, and this will be before we draw. Now, all that's really left to do is just look at the expression for p1 of x as x tends towards 0, as it tends towards infinity, and just see how the graph behaves. And so we can look at when x tends towards plus or minus 0, we know that this is obviously going to go to 0, and this itself is going to go to a very, very small value, which will blow up to infinity. And so we can say that as x tends towards plus or minus 0, y will tend towards plus or minus infinity. And so on this side, we expect this to tend towards infinity and this towards negative infinity. We can do the same as x tends towards plus or minus infinity itself. We know this value is going to become, go infinite, and we know that this value here is going to tend towards 0. And so what we find is, again, as x tends towards plus or minus infinity, y here, which we've denoted as p1 of x, is going to tend towards plus or minus infinity as well. So on the other side, this is going to tend towards infinity, and this is going to tend towards negative infinity. And so this is the sketch that you'll get full marks for here. So that's the first one ticked off. Now, the second question is very simple. It is a 1 mark question, as we can see, and it just says that show that this is true. And so we're substituting n equals 2 into this expression, and we're going to show that when you do that, we can rewrite it in terms of p1 of x. Okay, so let's have a look. So we write that p2 of x is this here. Very simple, we just substitute n equals 2 in there, and then we can rewrite it as this format here. We notice that this here is the same as p1 of x, and so we have p1x squared, p1 of x squared minus 2, and that's question 2. Amazing. So quite a nice, easy 1 mark question there. Now question 3 is also another 1 mark question, as we can see, and it's saying find an expression for p3 of x, so this is when n equals 3, in terms of p1 of x. Again, this is going to be nice and easy. We're just going to figure out what p3 of x is, which is this here. Again, all we've done is substitute n equals 3 into our form of pn of x, so we get this here. So I like to work backwards. So we know that we want to write this in the form of p1 of x. We know that p1 of x is this here, and so it would make sense if we want this in terms of p3 of x, we're going to probably have a cubed in there somewhere. And so what I did straight away was I said, well, let's look at what p1 of x cubed actually is. And it gives us, that's what it is. We can kind of factorize this out, and we find that it equals this. We can expand the brackets. Now I've done this in kind of quite a step-by-step approach, just so you can pause and take a look at what happens, but hopefully you'd be able to kind of look at this and immediately figure out that it equals this straight away. And so we find that p1 of x cubed is equal to this here, and we can collect terms and say, well, actually that equals p3 of x plus 3p of p1 of x, and so we can rearrange and find this form for p3 of x in terms of p1 of x here. And so we've got a nice 1 mark there as well. Now we have 2 final parts to the question, and they are both 5 marks. So we expect there to be a bit of work going into this. So the first question says, find all real solutions x to this equation. Okay, now hopefully you'll know if you've done mathematics that typically questions like this, they don't tell us to do stuff previously without a reason. And so we're going to have to look at, what we've done previously and how that might tie into helping us figure out what the real solutions are to this. So I've just rewritten out here. So this is what we wanted to try find the real solutions to. Now straight away, obviously in the question we've had a lot of 1 over, x, 1 over x squared, 1 over x cubed. And so to simplify this into stuff that we might be familiar with, I just divided by x squared. And in doing so, we get this form of the equation here. Amazing. Now, what you might notice is, well, actually, this plus this is actually p2 of x, and this plus this is actually p1 of x. And so we can say, well, this entire thing here actually equals p2 of x plus p1 of x minus 10. And we were told to find p2 of x in terms of p1 of x. So we can substitute p2 of x in terms of p1 and find this equation here. And what you'll notice is it's actually a quadratic equation in terms of p1 of x, which is pretty nice because we'll be able to hopefully find roots from this. So in doing so, we can then factorize. We find that we can actually rewrite it in terms of this. And obviously we can deduce from that, from here and here, that p1 of x is 3 and p1 of x, or p1 of x is minus 4. So those are the 2 solutions to this equation here, but they're in terms of p1 of x, and we obviously want them in terms of x. So let's substitute what p1 of x is and compute. So again, we just say, well, this is p1 of x, we know that it's equal to 3, or we have p1 of x is equal to minus 4, and then we just, basically multiply up. We find 2 quadratic equations in terms of x, and in solving those we find that x is equal to this, or x is equal to this. Now I should have probably put here that they were or instead of and, just because we obviously have different solutions there. But yeah, very nice. That's the answer. That's 5 marks to this problem. Amazing. Now the very last question in this now says, and this is one step harder because we have a 7th order polynomial here, and it says find all real solutions x to this equation. Now we know we're going to have something very similar format wise to this, so yeah, let's take a look. We've covered a lot of mathematics in this paper so far, from algebra to calculus to even geometry. And if you're looking to improve on your mathematics, or maybe you just want to learn something new, then I'd highly recommend checking out Brilliant.org. Brilliant is a platform where you learn by doing, with thousands of interactive lessons in mathematics, data analysis, programming, and even AI. Each lesson encourages problem solving, which allows you to play with concepts, and this is a method that is 6 times more effective than simply watching lectures. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/EllieSightHome or click on the link in the description, and you'll also get 20% off Brilliant's annual premium subscription. Thank you, Brilliant, for allowing me to continue making really cool videos like these. So I've rewritten it out, as you can see. Now there's quite a bit of work, but it's kind of a very similar process. So I rewrote this entire thing out here. And this is the form of the equation that we have that we want to find roots to. Now hopefully you can see straight away that x equals 1 actually holds for this polynomial, and that helps massively because we can factor out x minus 1. But you can try it for yourself, just substitute x equals 1 into here. I mean, I've done it here, and yeah, we find that it does equal 0, and so x equals 1 does hold. So we can factorise x minus 1 out, and we find this. And so the next step now is to essentially compute this. So we can do as we did before, and because we have x to the power 6 in there, we probably want to divide by x cubed, which is what we do. Divide by x cubed, we find this equation here. Again, you'll notice that this plus this is p3 of x, and similarly looking at the other terms, we can rewrite in terms of p3, p2, p1 and a constant, and then because have computed what p3, p2 are in terms of P1, we can substitute that back in. And so we substitute in, we get this form here. This does simplify to a nice little form here of P1 of x. Now we can factorise this in this form here. Now this is quite a tricky step to realise, because we obviously have P1 of x cubed. It's a little bit more complex than just P1 squared, which we had previously, and so this is quite a kind of tricky step to factorise. But hopefully once you realise that we can do that, we can solve for P1 of x and get these two values for x here, and so that is the answer to that question. Now, what I kind of liked about this question was that it walks you through it, and so obviously the first part of the question we have a sketch, which is typical in mathematics, helps us visualise how things are working, but it was nice because each of the questions followed on from each other, so we were using stuff that we'd answered in part 2 of the question in the final part, and I like that the final 2 parts of the question were very similar, just one was a little bit more advanced than the other. Yeah, I thought it was a really, really neat question. I'm going to be making some more videos on further problems, so if you're interested then subscribe down below. But thank you so much for watching, and I'll see you all in the next one.